Welcome to this recorded video for the Part B lecture notebook for the third module. This notebook will be covering loops. We will go ahead and import NumPy as NP at the beginning to make sure that everything runs. And the learning objectives for this Part B lecture notebook are to understand and implement for and while loops in Python. We will see some examples, and we will primarily focus on activities that involve for loops. We will also be introduced to lambda functions within Python, which is another way to create functions, although with different purposes generally than what we've seen with user-defined functions in the previous lecture notebook. We will also understand list comprehensions in Python, seeing several examples of that, and we will create lists from a combination of lambda functions and for loops. Now, there's really only one primary activity, a very prime activity within this notebook. There's also an instructor-led activity that should help you with this one. And then there's a summary. So while there's not too many activities here, that doesn't mean that there's not a lot to investigate on your own and even try making your own examples and edits to this notebook, which I highly encourage you to do. So while you might work through the contents of this very quickly, I do encourage you to take the time to study things on your own and go a little bit beyond what you see here in terms of your own explorations and experimentations as usual. Now, the syntax is probably not surprising. There's indenting. With a for loop, we would say for, and we would iterate something in a list. And then we would have some indenting, just like with functions. We have our colon as well. That's all necessary. We would do cool stuff in the loop, and it would all be indented in order for it to all be grouped together. Every time we iterate through the loop, things would be done. And then as soon as you stop indenting, that closes the loop. Oh, there's a typo I have there, so I'll go ahead and get rid of that. We stop indenting in order to exit the loop. There's no return like with a function where we can return something. This is just done in the code, unless we put a for loop or a while loop within a function. And we will see an example of that as well. The list that we're iterating through can be strings. For instance, you could have a Alpha, Romeo, Sailor, Foxtrot. You could have those as strings, and you could say for string in that, and then print that string. In fact, if you wanted to see this, this is an example that you could make. I'll do a code cell below and just show you for string in, and n, and I'm just going to make this is actually a tuple type because it's in parentheses, and I'll make strings here like alpha, and then Romeo. What else did I have here? Sailor and Foxtrot. There you go. So if I just go ahead and print the string and see what happens. Oh, there's a typo. Okay, I said print string. Let me print string. There you go. It printed Alpha, Romeo, Sailor, Foxtrot. It just looped through everything there, and you can, you could edit what you loop through. So nonsense. This is just some nonsensical example, and there you go. You see my nonsense is now in the middle of my loop. So again, you can go through and make your own examples. You can edit everything I have here. I highly encourage that. There's some key points that we will cover quickly. You can iterate over lots of different objects. List, tuples. I just showed an example of tuples containing the strings, dictionaries, and even sets, which we haven't covered. But we haven't covered all of these yet. In particular, we haven't covered sets. In many computational and data science problems, you will commonly use the range command to build lists of numbers for iterating. And so I provided a link here to the official Python documentation for the function range. The range allows you to specify a starting point and a stopping point. It does not execute the stop value. It's kind of like array slicing. You start here at start and you go up to, but not including the stopping iterate. And then you can also specify a step. So you can click on this link here to find the documentation. I'm just copying it here, and you can Google examples for that, but we'll also see some examples here. So for instance, in the code cell below, we check out the partial sums associated with the first 20 terms of the geometric series corresponding to 2 to the negative n. In other words, this is what we compute. S sub capital N is the partial sum where we sum up from n equals little 0 to capital N 2 to the negative n. meaning this notation, if you're not familiar with this capital sigma notation, this is a summation notation, and this just means that you would let n go from 0 up to capital N, and you would evaluate this expression for all of those and then add up all of the results. So you would get 2 to the 0, 2 to the negative 1, that's when little n is 1, 2 to the negative 2, and so on up to 2 to the negative capital N. So S sub n just denotes the partial sum for those capital N terms. In fact, capital N plus, there's n plus 1 terms because we're starting at 0. So I have code commenting here, and you might again want, I suggest places to refer to and everything, but let's just look at what's going on. I start my partial sum term. This would be my S sub capital N term, and I'm setting it equal to 0 initially. And then for n in range to 20, here is what we do. In fact, I need to, if I want n to go up to 20, I want to include that term. Based on what I just said, that needs to be 21. So, because based on what I said, this will go up to, but not include the stop value. So this goes from 0 all the way up to 20, because it goes up to, but not including 21. So you can, here, I'm going to edit some of this here. So this will be the version you get, which is corrected, but it's good to see some of these mistakes I have initially before I get the final version so that you can see how I correct them. And now you notice I just add 2 raised to the negative n power to the partial sum using an in-place operator. And then I print out the result as I go through this partial sum, this partial summation. And I'm just printing that this partial sum changed outside of the for loop because it's not like a function where this is some scope. There's some local scope to this. So this partial sum variable, even though I'm doing all this code involving changing its value within this for loop, I'm actually changing the value of it outside of the loop because the scope of this is occurring in the code. This isn't like a function where this partial sum variable only exists within a function. So let's run that. Here we go. So we're just seeing the partial sums when we first just have 0 to 0, meaning we just have 2 to the 0, which is 1. And then we have from 0 to 1, which means we have 2 to the 0, which is 1, plus 2 to the negative 1, which is 1/2. So 1 plus 0.5, 1.5, and you can just see what it's doing. And I imagine computationally you could guess this sum is converging to infinity, that if you were to sum up an infinite number of terms, the sum you would get would be 2. And then at the end, again, I'm just printing out that the partial sum that we got when we summed the first 20, right? And notice I got to the 20th term because I went to 21 right there. If I had only had 20 there, and I'll run that, I would have only gone to 19 because of the way the range function works. So I'll change that back. There we go. Now you can also iterate backwards within range. So I'll do that now. So I'm going to start at 20 and I want to get rid of all the terms in the sum. So I want to go from 20 and I want to go down to -1, which will go, so I'm basically counting down in steps of -1. That's what this is doing. This is determining the step. So I'm starting at 20 and then I will go to 19, 18, 17, and so on. It's kind of like what you saw with slicing with indexing arrays with negative numbers. It's kind of the same idea, but it's similar. And then I'm going to go, I want to do this all the way through the 0th term when n is equal to 0. So I need to put -1 here to make sure I get rid of the final thing. And then I'm using the in-place operator minus equals 2 to the negative n power from these partial sum terms that I have above. And so now to show this, if I sum from 0 to 19, that means that I took that partial sum and I subtracted off 2 to the negative 20. And here is this term here. 1, 2, 3, 4, 5 nines, and then an 8. So if we come up here, we see that's exactly what we have. That was the sum from n equals 0 to 19. Now I took this as my final result and I subtracted off 2 to the negative 20 to come back to this. And you can just see I'm basically removing a term at a time until I remove all of them to get to 0. So if this removes the last one. Okay, while loops. So the way a while loop works is you say while, and then you have a condition or set of conditions that are connected through ors and ands. And while the condition is true, you would do something cool. Notice the indenting again and the colon. All these things are the same. And then you stop indenting to say that you don't want any code that follows to be in the while loop. Now, what you need to do at some point in the while loop in order to avoid an infinite loop is you need to make sure that somehow you either break out of the loop or update the condition at some point to make it false. So we often use while loops for iterative methods where we are unsure exactly how many iterations a process should take. This happens, for example, when we look at fixed point or root finding methods, and we will see some root finding methods in the 4th module for this class. If the condition never becomes false, this will result in an infinite loop, so be careful. And so I say this again because it's very important. Be careful and avoid infinite loops. So how do you avoid infinite loops? It is fairly common practice in computational and data science to include some type of counter which tracks the number of iterations and negating the condition if the counter reaches a specified value indicating a maximum number of iterations is reached. Meaning, you might say, I don't know how many iterations this process may take, but I know I don't want to take more than 200. Maybe my conditional will turn false at the 2nd, the 3rd, the 4th, the 10th, the 20th iteration. I just know that I don't want to do more than 200 iterations. This is actually fairly common practice, not the number 200, but the idea that you would have some sort of counter and you would track the maximum number of iterations, or you would track the number of iterations versus some maximum number and then break. And you can exit from any for or while loop early by using a break command explicitly. And that will exit the innermost loop. And I say innermost because you can nest loops inside of each other. If you want to stop a current iteration but continue looping, for example, due to some particular event occurring within a loop that you are checking for with logic, you can simply use the continue command, and this will immediately where you want to stop a current iteration to then continue to the next iteration. So let's look at an example with a while loop where we are trying to iterate the following equation. X sub n plus 1 equals a times x sub n times 1 minus x sub n. We're trying to iterate through this until we arrive at an approximate fixed point, meaning we want what on the left, this x sub n plus 1 value, we want it to be approximately equal to x sub n. So we want the difference between consecutive iterations on the x sub n term to be really close to each other. We're looking for that value to become a fixed point, so that if you plug the value in on this side, it produces the same value over here. It doesn't update x sub n plus 1. That's what we mean by fixed point. So to determine when to stop iterating, we set a tolerance parameter as a small positive number, and we check when x sub n minus 1 minus x sub n is less than this tolerance. Now we also will have a maximum number of iterations. In fact, we will use the maximum number of iterations as a control in our while loop. And we'll continue to iterate while we have not reached our maximum number of iterations, which we have just set as 8 because I'm not patient enough to let this run for more than 8 iterations. We start with the first iteration, 1. So the first time we go through this, it's 1. The second time, it's 2. The third time, right, you get the idea. This is it. This is iterating. It's adding to your iteration number each time. And then as soon as this is 8, then we'll get our 8th iteration, but this will become 9. So the next time it runs, if it hasn't converged yet, this will be false and it will exit. I have a tolerance of 1 times 10 to the negative 8th. And here I set a equals 2 in this equation. And I have x new equal 0.49. Some just initial guess. That's our initial value of x new. And then here's what I do. I make x old equal to x new. And then I just update x new as multiplying. If you look at it, what I'm doing here, I'm just doing a mathematical computation that in kind of a shorthand that it looks like this. So I'm taking x new and I'm multiplying to itself a times 1 minus x new. So I took that and then I'm storing it as that new value. I check if the absolute value, I'm using the floating point absolute value function within NumPy to check if the difference between x new and x old is greater than my tolerance. So if that happens, these 2 points I'm considering too far apart. And then I just continue. Now, I have all these print commands here to point out you will not see these because of this continue command. This will just immediately send this back to another iteration. If I comment this out, then you will see all these print commands showing. So I'm going to run this twice so that you can see that. And then if this is less than or equal to the tolerance, well, that condition would then be false, and so then we would break. So let's run and see how this works. So after our 5th iteration, we see that the fixed point is 0.5. Let's see if this is actually true. So did things work correctly? If a is equal to 2 and we put 0.5 here, 2 times 0.5 is 1. 1 minus 0.5 is 0.5. 0.5 times 1 is 0.5. So it would just make 0.5 here. So we're done. This isn't going to update the x value anymore. And that took 5 iterations. Notice, even though there was 5 iterations, we never even saw that once. So if I comment out the continue command, now you notice I'm printing this information out each and every time. So why might you have a continue command and why might you have these print statements? It could depend if you're in the process of developing or debugging code and how you might want to try to control things as you're trying to figure out what the proper workflow is for your code, and if you're trying to isolate where problems might be. That might be a good time to use continue or comment it out if you're trying to get more information on whether or not things are going right with your code. So if I again and you can see my initial guess was 0.49. Then when I updated, it was 0.4998, and it keeps going. And this was at so this is the first iteration, second, third, and then in fact, I should say, because it exited, this would be iteration number -1, because I'm always adding 1 immediately. So it was actually after the 4th iteration. So there we go, I fixed it. So this will be what, again, you have for what I give you on Canvas. And if I I'll just comment that back in. And again, you notice after 4 iterations, again, it's correct now. Now it says it's 0.5. Okay, let us do this instructor-led activity now. Now, this might actually be a good time either right now to pause this video and then read through these instructions and try this activity on yourself. I provide some links to get you started. It's involving prime numbers. It's to set you up with your activity that you're asked to do. You could either pause this now and try it yourself, read through these instructions, or you could wait for me to read through the instructions and then pause the video and try it yourself and then check against what I'm about to do. Okay, so I'm not going to click on this link and read through things. I'm going to, because I know what prime numbers are. A positive integer is prime if the only divisors of it are 1 in itself. In fact, the positive divisors of it. So what I'm asked to do here is in the first code cell, create a function that checks if an input is a prime integer. And the code should do the following. It should check that the x value, that is, I'm assuming you're using x for the input of the function, is a positive integer. And it lets the user know whether or not the correct type of variable was received. So this would be, let's say if I wanted to call, first you have to name the function. I'd say, well, maybe check, I'll define it as is x prime, where I'm assuming I'm getting a value of x. And so the first thing that I would want to do is if it's not a positive integer, then nothing should be done because we only check if positive integers are prime. So you might remember from the previous lecture that we can use is instance. And this would be true whenever x is a positive integer. Or excuse me, whenever x is an integer, but I also need it to be positive. And if neither of those things happens, then I don't want to do anything. So what I'm going to do is say if x is not a positive integer, or excuse me, is not an integer and is not positive, then we will print something to the user. So maybe no. We only check if positive integers are prime, buddy. What are you doing trying to give me something that can't work? And then return. You can put a return right here inside this if, and it would just return nothing. It would just print that to screen. And then if this didn't occur, what I know is I can now print, great job. X is a positive integer, and we now check if it is prime. So I'm accomplishing the first part of this task, which is to check whether or not x is a positive integer and let the user know whether or not the correct type of variable was received. So that accomplishes the first part, this first bullet point right here. Now, if x is a positive integer, we want to determine if x is a prime number or not and output the following. If x is prime, we simply want to let the user know. If x is not prime, then we want to let the user know, and we want to return a list of all the positive divisors of x that are not 1 or x. Well, let's get to that. So we will check. You only need to check if a number is prime. You actually only need to check up to the square root of that number in terms of integers to find whether or not it's prime. But I also want to figure out what all the divisors are if it's not prime. So in that case, what I need to do is I need to start at 2, because I already know 1 will divide it. I need to, a 1 is always a divisor. We're trying to see if 2, 3, 4 other numbers less than half of x. So we go up to x divided by 2, and I got to do plus 1. Because remember, range goes up to, but not including this number. So by adding 1, and remember this double divide? I showed that in one of the very first lecture notebooks. That's an integer divide. So this will ensure that we check all the numbers all the integers starting from 2 up to half of that number to see if it divides into x. So you might, if you're not familiar with prime numbers, you might just want to do a little reading. I provided a link to the list of prime numbers. You might just Google like what is a prime number, but they're not all that complicated. It's numbers, it's only positive integers with the only divisors being 1 in itself. But if you wanted to read a little bit about them and just see examples, please click on some links and do some search. So after we have this search though, which is very much just deduced that we're going to check from 2 up to half of what that number is, we now need to check if x divided by I, it divides evenly, if I divides evenly into x. So what we check is, what is x divided by I? If it is equal to 0, so this is the modular arithmetic. This is asking what's the remainder of x divided by I. That's a modulo division, I should say. So you should Google what the percent sign does. I think I might have shown this before, but if I didn't, you can just say Python percent is what. You could check that in Google. Just here's modulo division in Python. The percent symbol in Python is called the modulo operator. It returns the remainder of dividing the left-hand operand by right-hand operand. So I'm just seeing if x gets divided by I and there's no remainder, so I divides into x. So if that happens, then what I need to do first, because I'm supposed to return a list of all positive divisors if there's any, and I want to return all the ones that are not 1 or x because I already know those are, I need to create an empty list. If this happens, I know I divides into x. So I need to append to my list I. Now I check if the length of that list is 0, then I know that x was prime. So then I can print, huzzah, x is prime. Else, I would let the user know x is not prime at all. Below are its divisors. And then I would print its divisors. And then I don't have to return anything. You don't even need that command, but I'll just have a return with nothing because it's nice formatting. So that is my function. Now I can check, is x prime? So what I'm asked to do at the end is show examples. Test it on, I provide this link for the list of prime numbers. The first, 1,000 or so, or first prime numbers up to 1,000 are listed, so you can check ones here. And so I'll just do some examples. We know, for instance, like 2. Oh, that is not prime. So I have a mistake, and I think it's coming from here. This is good. I'll fix this right now. So what is the problem with here? I'm going from 2 up. Because 2 is a prime number. What am I saying? Oh, get it together, Troy. There we go. 3 is prime. 2 and 3 are prime. 2 is the only even prime number. Oh man, what a brain fog I have right now. All right, 4 is not prime. We know it's a positive integer. We're going to check if it's prime. It's not prime at all. Here's this divisor, 2. What about 5? 5 is prime. What about 6? 6 is not prime. 2 and 3 divide into 6, for instance. What about 53? 53 is prime. What about 57? No, 3 and 19. And you can always check if you don't believe it. 3 times 19 is 57. So you can check quite a few of these. You could say, what about 157? Wow, that was prime. That was just a guess on my part. Is x prime? And then you could check, let's say 2501. X is not prime. 41 and 61 divide into that. And again, if you don't believe it, check. 41 times 61, 2501. Is x prime 5,763? No, that has many divisors, none of which I would have guessed. And you can, of course, check all these. Now, your activity that you're asked to do, and again, you could go to here and just check that, make sure that it returns on quite a few of these that they're actually prime, because these, I'm assuming Wikipedia is correct here. Your activity is to create a function called common divisors that has two parameters, x and y, which should both be of type int, and the function should check their types are correct. So you should define your function. It should have two parameters, x and y, and you should check if both x and y are positive integers. In fact, I'm going to say that, type int, and both should be positive. There we go. Actually, you know what? They don't need to be positive. I'm going to get rid of that. I'm going to make it so that they're integers. They can be negative as well. But then only check for positive divisors on them. That's it. So these functions should determine all the common divisors, all the common positive divisors of these two integers. Store the results in a list and return the result to the user. So you need to check what divides into x, what divides into y, and what of those two things that divide into both are in common. Those are the common divisors. So that is your activity. So you can use this as some inspiration for how to do your function. But I'm going to leave that kind of up to you. There's a few ways that you could go about doing this. I don't want to give too much away, but if you struggle at all, I have the office hours, I have the discussion boards on Canvas. I'm here to help. But I'm just going to move on from that. I just wanted to make sure that you do that. And I should say there's another point as well, and I'll just add it here. Test your function on some x and y parameters for which you know the answers to make sure it is running correctly. I didn't actually ever check, by the way, on my function, what happens if I try to check if like -4, yeah, we only check if positive integers are prime. So that part is working correctly. What happens if I had given it 0? Same thing. And what about like, so 5763.0? Again, no floats. It's got to be ints. So that it looks like that was working correctly. So you should also show things where you like if it should produce the right output, even if it was the function just saying I can't work on those types of inputs. You should also do that here as well. All right, a brief note on list comprehensions and lambda functions. Now, I provided links again to documentation within Python within a tutorial that goes over that I again encourage you to read and even do examples from that documentation. But we'll just kind of get into it here. We mentioned list comprehensions very briefly in the first lecture notebook for Module 2. The basic idea is to use a function or rule written within the list declaration to quickly construct a list by looping over some particular inputs. So the code cells below highlight the basic ideas using an example from the official documentation. Now, this is what I would call a clunky way of constructing a list. I first create an empty list called squares, and then for x in range 10, meaning I start from 0 and I go up to but not including 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I then append to it x squared. These are the squares. And then I will print the squares list. And so we see it is 0 up to 9 squared, 81. Now, the slick way of constructing a list is with what is called the list comprehension. Squares is equal to the list. Here's my square brackets, and here's my function. I want x squared for x in the range 10, meaning from 0 up to but not including 10. And you see it created the same list. It's shorter code. You can literally do either one. It's just you will sometimes see, either in my code or other people's codes, People will often do these list comprehensions as they get more comfortable in Python. I encourage you to try it out whenever you can and do multiple ways, and even try making your own examples here of that are constructing the same list but in different ways. It doesn't have to be squares. Maybe it could be cubes. Raise it to the third power and make sure that things work the same way. Or do whatever you want. Just make different types of lists in multiple ways. Now, imagine we have an explicit function defined that carries out a more complicated operation on transforming some input data x into a useful output data y that we want to use in our list comprehension to create it. So maybe we have a function that's a little bit more complicated than x squared. So for instance, here's my again, this is kind of silly, but imagine I had my complicated function here where I get an x value. Instead of just taking x squared, I take x to the 5th power. I subtract 2 times x squared, then I add x, and then I finally subtract 3. And that's my function. It's just some polynomial, but it's kind of nuts. And then imagine that I have some list of x values, my x values, where I say these are the values I really care about, and I want to produce a list of y values that corresponds to these. Well, here's my list comprehension. I have, again, look at the square brackets there. I put my complicated function of x for x in my x values, which is it's the similar syntax of x squared. That's like my function here was just x squared for x in range to 10. Here is this function of x for x in my x values. And it just loops through this list. Because remember, you can loop through just about any type of thing that you want. That's within reason. Tuples, lists, dictionaries, and so on. So then that created the list of y values. So now I have a list of x and a list of y values. I could plot them, for instance, if I wanted to. I'm not going to. But that would be a good thing I suggest for you to do, is review in Module 2 how to plot data and actually plot the x versus the y values here. And you could create from this, you could use this to plot x and y values against each other very quickly and look at this 5th order polynomial. So there was nothing really complicated about the function above. It was just a polynomial, and it is simple enough to be defined by a single line of code. So the question is, what happens when we do that? Like, why should I even define a function for this if maybe I only want to use this one place in the code? Well, I would maybe want to use lambda functions, and I provide a link here to documentation, not the official documentation, but some other documentation involving lambda functions. My favorite quote about lambda functions is this: unlike lambda forms in other languages where they add functionality, Python lambdas are only a shorthand notation if you're too lazy to define a function. I love that because mathematicians are notoriously lazy, so this is very appealing to me. Functions are already first-class objects in Python, this is still part of the quote, and can be declared in a local scope, and we talked about scope previously. Therefore, the only advantage of using a lambda instead of a locally defined function is that you don't need to invent a name for the function, but that's just a local variable to which the function object, which is exactly the same type of object that a lambda expression yields, is assigned. What does that last part mean? What is all this? It comes down to this. If you just wanted to use that computation of the polynomial for a little bit of time in a very localized area of code, then you might as well be quote unquote lazy about it and define a lambda function. So I would show this below, right? Instead of going through the trouble of making this user defined function with the define my complicated function of x and say what it does and return y, I could just say, look, make f equal to this lambda function. So now f is this function, and now I would just have, for my y values, the list comprehension would look like, with square brackets again, f of x for x in my x values. And it will produce exactly the same y values as before. And I actually want to show you, we don't even need to define f at all. This is where lambda functions are also called anonymous functions. So I could have a list comprehension that's just my y values, and I could put the lambda function in parentheses here, lambda of x, and I have the whole polynomial x to the 5th minus 2 times x squared plus x minus 3. Notice that after I say lambda x or whatever the inputs are to this anonymous function, the lambda function, you have the colon. I evaluate it at x, and then I say for x in my x values. So I never even have to define it as f. I don't really have to define it as anything. I never have to assign the lambda function to a variable. That's how lazy you can be. And again, it produces the same outputs. So The advantage in some sense of doing it this way is if you just have f defined here and you want to reuse the lambda function in a few places, you should probably call it f or something so that you can reuse it in a few places instead of copying and pasting this, because that ultimately leads to errors in code. It's kind of just up to you. There's no real reason to use lambda functions other than it's kind of looks slick. It shows you're confident in your coding. It's up to you, though. I'm not going to force you to do it, but you are going to see me start using lambda functions in Module 4 quite a bit. So I do have some other examples here, this last example. So let's just read this through carefully. I show another nice use case where a lambda function can help make code less clunky looking. See if you can add some comments to this code cell below to explain what is going on. So I highly encourage you to add code comments here. So this is kind of a suggested but not required activity. And I also suggest, and again, it's not required, for you to make your own lambda functions. Play around with this. Again, make it your own. Make the notebook useful for you so when you look at it in the future, you have useful comments and examples for yourself. So here I have this my other complicated function. So it's not my original complicated function, which was the polynomial. And again, it's not that complicated. I take using the built-in sine and exponential functions within NumPy, I take sine of x and I add to it the e to the negative 2x in the power, and I return that value. But look what I do with f. I create a lambda function now, and I don't know why I have that colon there, so I'll remove the space. So I have lambda x, and I say, well, I want my other complicated function to be evaluated on my first complicated function evaluated at x. So I have this composition of functions. Lord knows what the output of this is going to be. Yikes. So I have 403 point something, negative 0.98 stuff. I have 8 point something times 10 to the 231st power. There's a bunch of nonsense here. So, okay, that's what I have. I would have never guessed any of these values, but it just made the code kind of a little bit more readable than having to imagine writing this inside of here or creating a function that involved those compositions. So it just, it's up to you whether or not you want to use lambda functions. It's just another use case where that lambda function in this case uses some user-defined functions as part of its construction. So that might happen in your code. You might say, I have several user-defined functions that are the base for all the computations I want to do, but then I want to start doing compositions in different combinations of those functions, but I don't want to call them their own function because they're just combinations of previously defined functions. Lambda functions are a great tool to combine multiple user-defined functions for little functionality you might need at various places in your code. So that's the end of this lecture. The last thing to do is the activity, of the summary activity. And so that's it. And I have one more lecture notebook in this module. It's the Part C lecture notebook, and I'll talk to you there. Thanks for listening.